Alright, so now let's do a conservation of energy problem. So let's say that we have a mass of 5 kilograms is held against a compressed spring with a spring constant of 150 newtons per meter. The block is launched up a 2-meter tall hill. What is the velocity of the block at the top of the hill? So, what I did is I drew out a little diagram of our problem. So, essentially, we have this compressed spring, 1.5 meters, and then there's our block, and the energy that's stored in the spring pushes the block up this hill. And we're trying to find the velocity at the top of the hill, right? So the first thing we should do is draw some LOL charts to figure out where the energy is, right? LOL. So, we know that at the beginning of the problem, we have elastic energy, right? Just some arbitrary number of elastic energy, right? Now, we don't have kinetic energy or gravitational energy because if we set the ground down here as our point 0, it would not be gravitational energy. And it's not moving, so it's not kinetic. So it's only elastic energy, right? And then if our system is the Earth, the block, and the spring, we are not adding any energy or subtracting energy either, because we don't have any friction, friction pad here, and we're not adding any more energy into the system, right? So energy elastic has to convert into the final energy, which we would say is energy gravitational, about half, in addition to energy kinetic. Now, the reason that I know that there's kinetic energy at the top of the hill is because the problem says that there's a velocity at the top of the hill, right? And gravitational energy does not have velocity. It's kinetic energy that is focused on velocity, right? So now that we've got this figured out, we can basically set up an equation. We can say that energy elastic equals energy gravitational plus energy kinetic, right? So let's erase this. So, like I said, energy elastic equals energy gravitational plus energy kinetic. Now, I have all three. Here's energy elastic, here's energy gravitational, and here's energy kinetic. Now, basically, all we want to do is we want to plug in the information given to us in the problem, right? So, like, for example, we know that this K is our spring constant, so we can plug in 150. We know the delta X is how much the spring is compressed, so that's, where is it? It's compressed 1.5 meters. Carry on. We also know the mass of the block, and we know gravity, 9.8, and the height is also given to us too. And then we also know the mass, and what we're solving for is the velocity. It's kind of weird. I must have forgotten to write how much the spring is compressed. Well, it's 1.5 meters, alright? So, move this down. So, 1/2 times the spring constant is 150, and then the distance that the spring is compressed is 1.5, square that, equals mass, 2, mass of the block, times gravity, 9.8, and then height is also 2, height of the hill, plus 1/2 times mass, which is 2 kilograms, and then times velocity squared. We don't know the velocity, we're trying to find the velocity at the end of the block's path, right? So So what we can do is we can plug this in and simplify stuff. So on this side we get 168.75 equals 2 times 9.8 times 2, 39.2 plus, these two cancel, so just v squared. Now we subtract this over to the other side, minus that, so we get 129.55, right, equals velocity squared, and then we just take the square root. Velocity equals 11.382 meters per second. And that is how easy it is to figure out the final velocity at a point. These conservation of energy problems are pretty easy once you figure out the initial energy and the final energy, and then you just plug stuff in. Ooh, it's the end screen. Click on one of these links to be directed to that playlist. And don't forget to subscribe!